take a look at the scene in front of you, right? This is a picture from the surface of Mars from the Opportunity rover that's been roving around there for a very long time. Actually, the Opportunity rover is dead now, unfortunately, sadly, but it far exceeded its mission, as I'll show you in a moment. But take a look at this picture it took. This was just a few months into its mission. What do we observe here? A kind of flat, boring looking plane right here, just a sand covered surface. But then we have this concentrated ring of rocks, right, with a depression. What does that look like? It looks like it's probably some kind of crater. It looks like some kind of impact might have formed that. Something rammed into the surface of Mars, caused the rocks to be splayed out in a circular fashion around it, and then they've just been sitting there, right? And the only thing that can really happen to them at this point is there's a little bit of wind with a little bit of sand in the wind, basically mostly dust, very, very small particles, right? They're getting hot and they're getting cold, really, really cold mostly. And there's cosmic, radiation that's striking them. This is about all they get to experience each day, day after day after day after day. And yet what you're seeing in this image is, these rocks are kind of rounded. There's not very many sharp edges to them. What does that suggest to you? Well, that suggests that they may have been sitting there for a while because something has eroded them to the point where they're kind of smoothed off a little bit. Right? But yet there's still kind of a jumble of rocks here. All of this kind of paints a picture, right? I think all of us would look at something like this, and even if you don't know a lot about maybe geological processes and so forth, you'll get the perception that this is something that is, obviously the crater is younger than the other rocks that are underneath the crater, right? This whole plane here, this whole surface of Mars is some kind of layer of rock. And I'll show you in a little bit here that it's many layers of sedimentary rock. And then you have an impact that then causes some of those rocks to get disturbed, and then they experience additional changes as they sit on the surface. Okay, all that's just an introduction to say that what I want to talk about is our perception of age. I think we have difficulties perceiving age. So the real question here is, how long do you think this has taken? Like, how long ago do you think that an object struck the surface of Mars, creating this small crater? And this is a tiny, tiny crater on the surface of Mars. But how long ago? How long ago was that? Was this last year? 6 months ago? 10 years ago? 100 years ago? 1,000 years ago? 500,000 years ago, million years ago, 100 million years ago, right? Do you need a multiple choice test and select the one you think is the closest to the answer? You might also be asking yourself, like, how would we know? Like, were you there? Did anyone document this? Like, how would we estimate how old this is? Let's talk about some of these things. But mostly what I'm here today to talk about is just an observation I've made about the difficulty we humans have perceiving age, especially when ages become very long ages. And I've titled this, Perceiving Age, Students' Interpretations of the History of Craters on Mars, because this is a picture I showed to a group of students in one of my classes. And we had a discussion about what they were looking at, interpreting, like, based on your knowledge, what do you think might have happened here? And then pushing them a little bit further. But I'm getting ahead of myself. Let me get started. Let me go back to the beginning of my story. Our perceptions of the age of an object are frequently based on our common experiences with similar subjects, right? Most people have the ability to guess the age of children with very little prior information. After all, we've seen kids, maybe we've been a kid ourselves, right? We may call this ability to guess age our intuition, but really this intuition is a scientific method that's working automatically in our minds, right? Our perception of a child's age is shaped on our many experiences with children over our lifetime. You could say it's shaped by a lifetime of data collection of characters like height and behavior patterns, right? We're collecting that kind of data constantly, storing it away in our brains. And then when we see a child we've never seen and we don't know their age and nobody told us, we weren't there, we still have a perception of how old they probably are, right? It's the combination of many pieces of evidence that and our experiences with interpreting that evidence that we use to generate what we really could call is a reasonable hypothesis. I generate a hypothesis of how old somebody is. And one way I might test that is like, I ask them, like, how old are you? That would be a really good way to test that hypothesis. See how close I am. But what happens when we're confronted with something like really unfamiliar to us? That's why I started with this picture of Mars. If we don't have any experience, right? And we could call that your common sense. If you don't have any of that common sense to guide you, how can you generate a reasonable hypothesis to explain what you're seeing? The concept of the age of the Earth is just such a concept. It's really difficult, I think, for people to wrap their minds around it because our ordinary experience doesn't allow us to easily comprehend the idea of millions of years. It just doesn't. We work on days, weeks, and a few years. A few years ago, I taught a course for our honors college at my university. And the class had 18 students, and they were all from very diverse disciplines. Just a few of them were like biologists or geologists. And one of my learning objectives for this course was to have students improve their sort of critical thinking skills while engaging in subject material of the historical sciences. Right, this was a seminar course with a very much of a discussion sort of format. And the theme was actually the history of the Hawaiian Islands. Like, what can we learn about the origins of the Hawaiian Islands and how they came to be? And what do we learn about a variety of different scientific subjects as we're exploring that particular question? So we were gonna discuss the geological history of the origins of the islands and the origin of the flora and fauna as well. So at our first meeting, I gave the class a homework assignment. All right, and that homework assignment was that each day they had to visit the Mars rover JPL NASA website, and they had to look through the recent like raw images that were just downloaded from the Opportunity rover. This rover that you see in the foreground in this picture right here, that was traversing across the surface of Mars, right, and did so for more than 10 years. And at the time I did this seminar, had been there only for, I don't know, maybe 6 months to a year. And so it was very active, seeing new things all the time. So you could go to that website, and I did like almost on a daily basis, like, yeah, what's the newest picture today? It roved a little farther, and like one day this was a picture that came up, and I grabbed a screenshot of this, or I guess I downloaded this image. Right? So what did they have to do? The students, this was what they had to do. It was my first assignment. Sort of like come into the class, they don't know what's going on. Here's what you have to do over the next before you come back again. They had to select one image, and then they had to write a one-page description of what they hypothesized was the history of the scene in that image, right? And I told them they had to include a timeline of when the historical events occurred, right? So in their historical narrative, they had to suggest a potential timeline of like how old these different events were. So in the next class period, which was about a 2-hour time slot, I had them send me all their pictures. I presented each of their images, right, to all the students, and I had them briefly go over what they proposed their timeline was and told their other students. And I had those other students ask questions and had them sort of like provide their suggestions for how they could improve their timeline of those events. Basically, I was asked, who's skeptical of like what that person said and why? Like there was engineers in the room, and they might suggest some reason. There's people of other diverse backgrounds, and they would bring their sort of general knowledge, common sense of things that they had learned in order to say like, I don't think that could be true, because how would that happen? Because there's this force or this thing happening, or you'd have to have this happen before that. You can't have the layers of rock form after the crater was formed, right? So that's just a basic geological concept. So most of the students, they selected images that included a crater. I mean, we're drawn to images that have some interesting feature on them. There was one student who just picked like a vast plain where it's just sand. Like there was like nothing going on. I think they just wanted like the simplest possible timeline, which is like, I can't know anything below about what's below the sand. So there was like something made the surface and then wind brought in sand and boom, there's sand there. When that happened, could have been yesterday or could have been 1,000 years ago. But most other students pick things like these craters. So the typical historical timeline that then they produced, they suggested included the formation of the bedrock, then an object striking the bedrock, and then the erosion of the crater, right? Such that it remains to be seen like in what it looks like today, right? The present day image. So the basic principles of stratigraphy or superposition, they seem to be pretty intuitive among the students. They really got that idea that certain events have to occur before others. There's a historical sequence that must happen. Not all the features in a geological formation could have occurred all instantly at one time. They all understood that the scene they were witnessing was, again, a whole series of historical events. But their intuition totally broke down. I mean, just completely was broken when it came to proposing how long each of these geological formations would take to form. The most glaring failure of common experience or intuition was their estimates of the rate of erosion of rock formations. How long did it take for this crater to get to the point that it does today? From the point where impact created these rocks, all right, this jumble of rocks, but then how long did it take for those rocks to erode to the point where we see them today? We got a lot of answers that were like, 10 years or like 100 years. Some even pushed it out to like possibly a couple thousand years. Nobody was talking about hundreds of thousands or millions of years for any of these things. So let me take you through a couple images. And just to give you a sense for like what some of the possibilities are for a sort of a historical progression of things. And then we'll come back and we'll talk a little bit about the dating of those. So all these images I'm going to show you are taken by the Opportunity rover and provided by JPL and NASA. Your tax dollars hard at work. And so because their tax dollars are also free for use in like what I'm doing here. All right, this one's kind of boring looking, but this is actually the landing site for the Curiosity rover, not the Opportunity rover. This is the Curiosity rover that landed in the Gale crater. And it landed in such a way that there was a rocket-powered lander that hovered over the surface, and then it lowered down the rover and dropped it on the surface, disconnected, and then the rest of the rocket lander thing flew off and crashed somewhere else. But as it hovered, right, it's creating a huge amount of force, wind downward against the surface, which then blew away the dust off the surface. And this is what you're looking at here is this area right here is the sand has been blown off of the surface rocks. But what I want to point out here is there is this angular rock right here. There's these sort of whitish rocks, right? You see these much harder, smoother rocks that are a little bit darker. I mean, this one has a little red dust on it, but it's darker nonetheless. And then you have right over here, there is a round pebble, a round rock. And I believe that's 4 or 5 inches in diameter. And so that, if you know anything about geology, suggests there's multiple different chemical compositions of rocks at this one location. And the rounded rock, given that there's many more angular rocks in the same location, that rounded rock probably comes from a different source, right? It's been subject to some kind of erosion, possibly in water versus wind erosion. So this seemingly bland image suggests that there's actually a fair amount of history in the types of rocks that are found at this particular location. Now, we can't see down into the rocks to see if they're layered or like anything like that. So this is a pretty simple one. And then you have something like this. This was another image, by the way, that one of the students picked. And I knew about this particular image, and I was really happy that one of them picked it. Because I remember the day that I was, on the JPL website, and I remember looking at the new images, and I saw this one, and I knew immediately what it was. I said, that is a meteorite. In fact, it's not just any meteorite, that is an iron meteorite. And then later I found out that they went up to it, took a look at it, and with one of their instruments, basically touched it and determined, yeah, this is like 98% iron meteorite that's sitting on the surface of Mars. Now, how do I know it's a meteorite? Well, for one thing, there's nothing else in this picture, right? It's all sand. There's no obviously large, like hard rocks on the surface. And so like, where did it come from? I mean, one hypothesis would be like, hey, there's a volcano like somewhere over here and it's spewing, and a piece of molten lava came flying through space, hardened, and then landed at the spot. And this is actually just basalt, right? But them finding out that it's not basalt pretty much removes that possibility. Also, there aren't any actually obvious volcanoes in this area at all. And so it was really hard to determine, like, where would this rock come from? I mean, who dropped this rock right here? It's like, are there aliens wandering around with rocks in their pockets and just dropping them in different places to trick us? No, the simplest explanation is that the way you get a rock like this on the surface of Mars is if it came from outer space, right? And plop, came down there. And it might have landed somewhere nearby and bounced over here. All right, there's actually no crater here. So it might have hit the sand, or it's more rock has eroded and it was there from some previous time and now is being exposed. All right, then there's this little enigmatic little indentation in this sand dune. All right, this is a kilometer away or so from the picture I showed you before. And here we have the surface is mostly covered by these sand dunes. Now, you might be thinking these are like really soft sand dunes and like the wind is just blowing the sand by, but actually they're kind of crunchy. By crunchy, I mean that when they drive over them, they have a hard crust, and then the wheels sometimes kind of fall through that crust. And that suggests that these are slightly cemented together. So the sand dunes have been sitting in the same place for so long. And there's been so little movement of sand that the particles themselves have become slightly cemented together, or at least they've settled to the point where they're more compact and sort of hold on to each other a little bit better. Well, so now what else are you seeing in this image? Well, there's this little indentation, right, which is I think like 6 or 7 inches in diameter. This is most likely a micrometeorite impact site. So just a tiny piece of like a sand grain flying at very high rates, right, from outer space, whacking the sand dune, and then boom, this is not what do you call those, ant lions, right? That dig the holes in your yard in the dust in order for the ants to fall down and slide down into their open mouths. We don't think that those exist on the surface of Mars. So this is an inorganic process that it caused this. Now the question becomes, how long has it been sitting there? Well, I didn't ask that question about the other meteorite. That other meteorite might have been sitting there for a year. It might have been sitting there for 1,000 years. It might have been sitting there for tens of thousands of years, right? Possibly longer, but we'll say 10,000 years is no problem for that previous picture. Now this one, maybe this might have been yesterday, but it could also be a year ago. It could be 10 years ago. It could be 100 years ago. Now there is enough wind and there's enough dust moving around that likely after thousands of years, you're going to see this is not going to look as pristine. You still might see like a slight indentation, but this looks fairly deep. And so it looks more like something that has occurred in the more recent past. And then, yeah, look at this. There's the tracks of the rover itself. Now, this is a great image because we have three things in this image. Well, really four. We have the original bedrock. So that bedrock had to be laid down at some point, and it is multiple layers of sedimentary material. Likely under like maybe a shallow sea. But it is a lot of basaltic sand. So it could be windblown layers to some extent, but it doesn't. But based on the walls that I'm going to show you later, it appears that they're probably more like water laid down. So you have the original bedrock. Then you have, off in the distance here, you have I think this is the Encounter crater. And the Encounter, or this might be Victoria. I'm getting my craters mixed up all of a sudden. And that particular crater is several hundred meters wide. And then you have this crater in the foreground. And I think any person looking at this would come to the conclusion that one crater is older than the other. All right. The one in the background, that huge crater, you see that there isn't like large rocks lying around anywhere, right? It's totally smoothed off. In fact, this entire surface you're looking at that looks smooth is probably a jumble of rocks from the past, because this whole area is a little bit higher. We're basically at the lip or at the edge of this other big crater. And it's actually raised up compared to what's farther away, which is where the bigger sand dunes are, because they're at a little lower elevation. And so this whole area is actually the rim of this crater. But you'll notice that there aren't any rocks sticking out because the whole thing has been smoothed off. The rocks have been completely smoothed off by eons of wind blowing across here and smoothing it down all the way down to a flat plain. Amazing. How long is that taking? I mean, it's suggested that based on erosion rates, this is hundreds of millions of years, right, to create the scene that you're looking at back here. But then you have this younger crater, right? This is obviously a younger crater, right? Something whacked the ground right here, a small rock. You know, it doesn't take very much when you have high impact, right? A small rock whacks the ground right here and causes some of the material to be lifted out and placed on the surface around it. So now we have these individual shattered pieces of rock, and you notice how jagged they are, right? That jaggedness tells you that they're pretty young. Now, I just said pretty young. Like pretty young could still be thousands of years old, maybe even tens of thousands of years old. But, you know, I would say it's also possible this is only hundreds of years old at this particular location. So we have bedrock, crater, a large crater, massive amounts of erosion that have occurred, and all that erosion had to occur before this smaller crater occurred, right? So you have large time gaps between these different events. So now we're back to our other relatively young crater. Now, this crater is definitely older than this one. This is the youngest crater by virtue of the fact that it has the most jagged rocks that are sitting high up on the surface. They have yet to be eroded down or other material placed around them or starting to cover them up, and the hole barely has anything in it, right? And then we go to this, in which we have clearly a jumble of rocks, of material that was excavated by the impact. But they're also kind of smoothed off. There's no jaggedness here. And so this is potentially hundreds of thousands of years. Hundreds of thousands of years. Remember, you don't have water to erode this. You don't really have any active chemicals in the atmosphere. You have wind, but it's not very forceful and it can't carry a lot of material. And so the erosiveness of the wind is very little. Yeah, and then you have this. This is Endurance Crater. These are all craters viewed on the same trip by the Opportunity rover. The Opportunity rover lands in one very small crater called the Eagle Crater, and it eventually traverses across the surface of Mars. So, I don't know, something like 15 kilometers or more. Amazing how far it got, given what its original timeline was. And so here it comes to a crater that you can see the edge of this crater is higher than the plane around it. So this must have been a large amount of material. This is 350 feet in diameter and 66 feet deep. And the edge of it is probably 30 or 40 feet higher than the surrounding plane. And so all this material around the edge is rock that was pushed out and, well, lifted up and exhumed and placed on top of the other rocks that were there. So you're taking rock from the middle and you're basically splaying it out over the surface of Mars. And then wind is eroding it such that there's no, again, there's no jagged rocks around the edge here. That's all smooth off to the top. Again, this is millions and millions of years of erosion at this particular location. This is seeing that same crater from a distance away, so you can see the edge of the crater. And the reason you can see it is because it's higher because of all the material that once surrounded this particular crater. But it is being eroded down to nearly the planar surface of most of the surface of Mars. Now, this is also Endurance Crater. Now, the rover itself, there was an area where it was wasn't very steep, and the rover was actually able to go down into the crater a little bit and be able to take these pictures showing these sedimentary layers. Now, this dark layer right here is probably the upper layer that represents like the rock that's across the plane, like the surface of most of the area around it. And then all this lighter colored rock on top of it. And you notice that it isn't really layered. What that rock is that's rock from down here in the crater that was thrown into the air and landed on top of the surface rocks. And so all of this material up here was just a giant jumble of stuff. And then wind has eroded it and flattened this off. Oh, this actually isn't flat, but this is on the inner surface of the crater, so it's not getting as much wind. I already showed you the picture on the other side where it's all smooth on the other side. And so what was neat about this site is they were able to investigate the rocks at, some 50 feet deep versus the surface rocks, because they didn't have to go all the way down to the bottom of the crater, because they could examine the rocks on the side here for a little ways down, but then they examined the rocks up here, and some of these rocks represent rocks from the bottom, right? They represent sediments from way down there. So they're getting more of the history of Mars by looking at this particular location. All right, and then we keep going out, and now we're gonna visit Endeavour Crater. Right, Endeavour Crater is a 16-mile wide diameter crater that is really eroded, okay? I mean, 16 miles wide. To make a 16-mile wide crater, that was a massive, massive impact. But this is all it looks like today, right? This shallow valley, and then you have these mountains that go all the way around the sides. And these mountains are hundreds of feet high, completely eroded. I mean, not completely eroded, otherwise they wouldn't be hills anymore, but smoothed off what once was probably twice the height that they are now. They're eroding, and the material's eroding down into the inside of the crater, which the crater was probably much, much deeper in the past, and now is very, very shallow from there. All right, so that's giving you some idea of sort of like different ways to look at historical events that have occurred on Mars. And also I'm stressing the radical differences in the ages of different places. All right, so back to my story about the students. I think that they could look at an image that had 3 craters in it in one image, and they could see, actually I can go to the next slide here. Yeah, this is Endeavour Crater right here, the 16-mile wide crater. So here's the mountain range around the side of what was probably a very large sound. And then you notice that everything is pretty much smooth around it. But anything that struck and hit and made this large of a crater must have dumped a large mass of material across this entire plane. And so the rocks that are in this plane are probably all smooth off stuff of material that was laid down there. And so you have craters, like this crater has it's sort of sharp edges to it, whereas this crater is completely eroded. And there's different size craters. But these craters are obviously of different ages. Victoria crater I didn't show you, but Endurance crater is just that little tiny speck. The one I showed you that the rover actually went down into, that's 60 some feet deep. And so just that gives you a relative size difference. Endurance crater versus Endeavour crater. And then the original crater it landed was Euclid crater. So this is the path that the Opportunity rover traversed. It went all the way up to the top of this mountain over here. And so covered a good bit of ground on the surface of Mars. Well, back to my students. All right, there wasn't a single student that thought that any of the craters were more than 100,000 years old. Out of those 18 students, none of them, like, they just couldn't believe that they could be more than 100,000 years old. Most of them said they would guess that the youngest looking crater was maybe like just a few years old, like maybe 100 years max. They thought that the largest crater that had the younger looking craters inside, I mean, Endeavour crater has craters inside, and I didn't show you Victoria, but Victoria has 2 craters on the side of the Victoria crater that are obviously much younger than the crater itself. And they thought that because there was younger looking craters that also experienced erosion, so they had to be like maybe hundreds of years old, then they figured that maybe the other crater, which looked really eroded, maybe that's like 100,000 years old. Right? Then I had the students like debate among themselves about like, okay, so what processes would be responsible for eroding these rocks? We've already talked about those, right? But I asked them to figure out like, so what's happening here? Like, how did they become eroded? And they quickly concluded like, it's got to be like mostly wind. Like wind has to be the primary force on the surface of Mars that's causing erosion. But even after they figured out that wind was the primary force, they just couldn't convince themselves that what they're seeing was the result of wind erosion. And they just found it difficult to comprehend that these craters were likely more than 100,000 years old. Right? That very first, like fresh looking crater I showed in the very first image, like Mars geologists think that's got to be at least 100,000 years old. Right? That's like kind of the minimum age they put on that. 100,000 years. Just to get to that point. And the Endurance and Endeavour craters, 100 to 500 million years old. Right? This Endeavour crater right here, that's 500 million years of erosion to erode it down to its present appearance. Right? Now, my students, I think many of whom are engineering majors, they really only thought it would take like 1,000 years to erode most of the rocks that they're being shown in the pictures. Right? As we continued to proceed through the class, eventually I discovered there was only 1 out of 18 of those students who had any sympathies to like what we call like young Earth creationism, that the Earth is young, or that the universe is young, which means also that Mars is young. So, so the students didn't have some sort of bias against thinking that Mars was billions of years old. They just simply couldn't fathom the time required for wind to cause this action. Like throughout the course, we kept coming back to these craters. We'd look at the evidence for the present and the inferred past wind speeds on Mars. We looked at some of the papers just briefly of like actual estimates of the physics of like how much material could be held inside of the wind, the air column on Mars, and then what the abrasiveness of that material would be. And so estimates of like how many times would you have to hit particles on the side of the rock, especially some of these basalts, which are probably pretty hard, in order to erode those rocks. And another video, we had mentioned that, there's a general estimate of like maybe a half an inch, right? A half an inch of erosion, maybe per 1,000 years. That might be like a pretty good rate. So we asked like basic questions about how much dust could be suspended and all that stuff. Finally, the concept of the rate of erosion on Mars being really low, right? At the time, that finally kind of started to get hold. But it took like weeks of looking at the evidence and thinking through the processes to sort of like allow that to marinate in the students' minds for them to really start thinking, man, these are pretty old stuff. I'll really never forget like the initial utter disbelief of these students that this landscape was like super ancient, right? Just as they looked at me like, what are you talking about? That's probably just like tens of years. I literally had students who thought that most of these craters were like, one of them was a year old, and then other ones might be 10 years old or maybe 25 years old or something like that. So it was a reminder to me that many of the concepts of science that are like so obvious to scientists, right? They're really just not obvious to the majority of the public. So as a result, you can have creationists like Ken Ham. They use these common misconceptions or the lack of the ability to have common sense for things like ages, right? They use that to their advantage because they can simply confirm to their audience what they probably already think. Hey, these features can all be squeezed into 10,000 years or 6,000 years. I mean, after all, 6,000 years itself seems like a long time to, especially to teenagers, right? Yeah, 6,000 years. I mean, 10 years seems like a lot of time, and a lot of things happen in the world in 10 years. And even students have some sense that a lot of erosion can happen in 10 years on the Earth. And so it doesn't seem inconceivable at first to think of these objects as being just a few thousand years old. But alas, it really doesn't appear there's any way that they can be that young. Because there isn't any known mechanism to cause them to go from what they must have looked like originally upon their formation. I'm specifically talking about craters here, to their present state. It's an awful lot of erosion that has occurred. And in my other videos, I mean, you're going to see we're going to look at other landscapes, hills and valleys and sides of mountains, where we're going to see tremendous amounts of sedimentary rock that has eroded. Well, first of all, it all had to have been constructed, and then it's all had to have been eroded as well. And you stack that on top of each other, and you end up with enormous amounts of time required in an environment where there are very few forces available to you to be able to accomplish these type of topographical changes on the surface of Mars. So when we look at Mars, we're looking at something that is as I said in one of my other videos, can you spot the difference? If you were to go back 1,000 years and take this particular picture, if I had a satellite, right, circling Mars 1,000 years ago and it snapped a picture, it almost surely would have looked virtually identical to this picture. If you were to go back 1,000 years and stand in this particular position and take a picture, right, I think that crater likely would have looked pretty much just like it does today. Oh, and by the way, you see the tracks there, right? So the Curiosity, the Opportunity rover passed by there. You can see where it turned around too. It has 6 wheels and it can do little loops. It's been 15 years now or so, and now with satellites we can look down and see the tracks. We can trace the whole pathway that the rover has taken on the surface of Mars 15 years later. That should tell you something right there about how much wind and sand are being moved around on the surface, at least in this particular location. We know there are areas, we know there are places on Mars where material is being moved around at a greater rate, especially near the poles. But at least at this particular area, the evidence suggests that there's not a tremendous amount of motion of material. And so the wind forces are not that useful. And I should, to be fair, I will add that it's not as if there wasn't higher winds in the past. We know that Mars has, just like the Earth, experiences over hundreds of thousands of years changes in its elliptical motion around the sun, right? So sometimes a little farther, some a little closer. Also, the planet itself is tipped and that it precedes, and so sometimes it's tipped more than others, and that changes the climate on Mars. We know that the climate changes. And there are probably times in which, under some other climatic conditions, there's more wind and more transport. But we're not talking about like 100,000 years ago, there being like it covered with water, not that kind of climate change. We're talking about colder, warmer, a little bit windier, more dusty, less dusty type of thing in terms of changes occurring. That's not going to significantly change the erosion rates, at least not the amount of the erosion that we needed to make this into a 6,000-year-old surface. Not nowhere close to that in terms of erosion rates. All right, so if you want to know more about that and young Mars creationism, I've talked about that in a couple of my other videos in which we talk about young Earth creationists trying to employ a global flood on Mars to try to explain these features, which this picture itself kind of tells you that that's not going to work. All right, a global flood could maybe lay down the layers of rock that are here as the primary rocks, but a global flood doesn't explain the craters. All right, and the crater would have to have happened after the layers were laid down, and then you'd have to have erosion after that. Well, the flood's already done, so you don't have the water to do the erosion. You have wind. That doesn't help you. Doesn't really get you any closer to explaining this particular image that's in front of us right now. All right, so I'm working on, like I said, a couple other videos on Mars showing different places and different rovers that are in different locations on Mars, and sort of going through and looking at images that have come back from Mars and talking about what they tell us about how we understand the age and history of this planet, and then relating that to questions about the age of the universe and solar system. All right, thanks for hanging out with me. We'll talk to you later. Bye-bye.